basically what we are going to do today. Let's say I have a certain population from which I pick different samples. What is the difference between a population and a sample? Difference between population and sample. Yes?
The sample, a population is like everyone. A sample is a small portion of everyone.
Yeah, small portion. I like this. The small portion of everyone. So let's say if I'm doing a research about the high school, my high school grad students, so my population will be all high school grad students. And if I'm going to do a research, I cannot, for example, for any reason, for money reasons, for efforts, whatever, cannot pick everyone. So I'm going to pick just a sample of the high school grad students. So let's say I'm going to pick only 50 students of high school grad students, and that would be my sample size. Okay? So basically what I'm going to do today, I'm going to test if I pick a sample from a certain population, does this sample really belong to the population that I picked it from or not? Meaning, let's say I have a population, or I have picked different samples. Let's say I picked 10 samples, okay? And I'm looking for average of rotten eggs in a basket. Okay, like let's say basket of eggs, and I'm looking for rotten eggs in this basket. Okay? So the first time I pick a sample and I look at the number of rotten eggs, I get a 10. Second time, I get 12. Third time, I get 10. Fourth, 11, 12, 10, 11, 12, whatever. Okay? I picked all these samples and I'm going to draw a distribution of these samples and look at the average of the means of the different samples. Okay? And let's say I get an average of 10. Okay? So I'm going to look what I'm going to test today, or the hypothesis test that I'm going to look at today. I'm going to look at whether the mean of the sample that I got here is picked from a population which has a mean of 10 as well or not. Meaning, let's say that this is my population, okay? And mu here is the mean of the population. That's why it's called mu, because it's mean of the population, okay? And let's say I pick a sample and found that this sample has a mean of, so let's say mu of the population is 10. Okay? And I picked the sample and I found that the mean of this sample was 12. But 12 actually can come from a population of mu of 10. Same like I showed you. Like if I pick the first sample 10, second sample 11, third sample 12, and then 10 and 10 and 10 and 10, I might end up with an overall average, population average of 10. So a sample of 12 can come from a population of mean 10. So basically what I'm going to study today, does this sample, or to test the hypothesis of, does this sample that I picked come from a population of 10 or not? Meaning, does it come from here, the area that is in the middle here, or does it come from the areas where you usually reject the null hypothesis, these small areas? And you remember last time we did together the p-norm and stuff in order to know the area under the curve. And I was telling you then that if you have the area under the curve very small, that means it's something towards the tail. That means it's something that's probably rare, or that it doesn't belong to the population. So basically what I'm going to study today, if I'm picking a sample, this is the whole population with different samples. If I'm picking a sample, does this sample come from the area in the middle here, or does it come from the peripheries? If it comes from the area in the middle here, that means it comes from a population of mu 10. If it doesn't come from this area and come from here, let's say, that means it doesn't belong to this population, and maybe it belongs to another population here, but not to this population. Okay? So this is basically what we are going to do today. I'm sorry, I actually promised not to explain any theoretical part, but I told you, like this one, I thought I really need to explain a very tiny theoretical part at the beginning, just to tell you what we are doing here today. What does it mean I'm testing this sample against the population mean? What does this mean? Signify? A lot of means here. What does this signify when I say, okay, is this sample mean? I got a sample and the sample mean was 13. Does this sample mean of 13 belong to a population of sample mean of 20, for example, or not? This is basically what I'm testing. Okay? And I'm testing two things. I'm first testing whether it belongs or not, like this is basically equality. Equality, like does it come from population which means equal to 10 or not? The second thing, this is actually the first exercise that we are going to do together. The second thing is that I'm not testing equality. So equality, I'm basically testing, does it come here? Equality is, I'm basically testing, does it come in the middle or not? Meaning, it doesn't come here, nor there. It doesn't come in the two tails. Okay? But I can also ask, does the sample mean, is the sample mean greater than the population mean or not? Or is it less than the population mean or not? Okay? So the first thing, I ask whether it's equal to the population mean or not. The second thing, I'm asking a different one. I'm asking, is it smaller than or greater than? What's this smaller than or greater than? Basically, does it lie here, smaller than the population mean, or here, greater than the population mean? So basically, I'm testing either one of the two things. So that's why the first test of equality, is it equal or not equal to? This is called a two-tailed test. Why two-tailed? Because I'm checking whether it's equal or not from both sides. But the second one, greater than or less than, this is called a one-tailed test because I'm checking either less than, which will be your left tail, or greater than, which will be your right tail. Okay? So this is called a one-tailed test. Okay? The most common test is called the t-test. You're not taking t-test, or you didn't take the t-test yet, and you're going to take it after the midterm. And that's why I'm going to actually use with you today something else called the z-test or z-test. Basically doing the same thing like the t-test, which is testing the sample means against population means with two weights, two tails and one tail z-test. Okay? So let's go and read the examples. And so question one is related to two-tailed hypothesis testing. So this is basically equal or not equal. And the second one is related to greater than or less than. Okay. So the first one, two-tailed hypothesis testing equality. So the question is saying we want to test with 95% confidence interval whether the volume of a shipment of lumber is as usual, mu is equal to 39,000 cubic feet, and sigma is equal to 2,000. So these two figures, mu and sigma, they belong to the sample or population. And this is usually the first question you need to ask yourself, like what are these numbers related to? 39,000 sample or population? Population, how did you know? Yes, they do, actually both of them, they do belong to the population. Two things, you can tell from two things. Okay, the first thing is the terms. Mu and sigma are terms used with population. The mean and standard deviation are terms used with the samples. This is one thing. The other thing is actually I'm saying the volume of a shipment of lumber is as usual, whatever. So meaning the standard is this. The standard is standard of a population, not standard of a sample. Because sample is something you just take once from a population and maybe next time you have a different sample. But when I say as usual or in general or whatever, this is something that is related to the population in general. That tells you that this is the mean of the population and the sigma of the population as well. Okay? So I'm telling time just to produce random variables of a normal distribution. To generate 75 shipments with mean 36,500 and standard deviation 2,000. So here these two figures, are these figures for a population or a sample?
For example,
For example, yeah, this is very clear for different reasons. First, I told you to generate a 75 shipments, so that means it's just one sample, like of size, the n of the sample is equal to 75. This is one. Second, the terms are saying mean and SD. This is mean and standard deviation. These are terms used with samples in general. Okay? And I'm telling you also to use a command set seed, which we took last time, in order to have all of the results are the same, because we are doing randomization here. So we don't need each time that we run the code to get different numbers. So I'm telling you set seed 0 before R1 to regenerate the same data as required. And now I'm going to create my null hypothesis and my alternative hypothesis. Very important. Null hypothesis always have equal sign in null hypothesis. You never put another sign that is greater than, less than, not equal. You don't put that in the null hypothesis. You put that in the alternative hypothesis. Okay? So my null hypothesis is basically I am testing whether the mu is equal to the population mean or not. So basically mu is equal to 39,000. I'm testing against the population. Huh? That's why mu equals 39,000, not mu equals 36, whatever. Because I'm testing against the population. The alternative hypothesis, here I can put the non-equality. It's basically in this one, it's easy because if it's not equal, it's not equal. So you put mu not equal to 39,000. Okay? Just the opposite of the null hypothesis. Okay? And it's telling you find the test statistic, the p-value, and the 95% confidence interval. So let's see how to do that in R. Now you can go to the .R code that you have, and you just right-click and open in RStudio. So maybe your computer is done by default now that it will automatically open with RStudio. Okay, in order to run the Z-test that I told you, you need to install a package. I told you packages are actually a set of code that is written in which there are different functions. So sometimes you already have the functions in your packages that you have, but the z.test function is a function that requires a certain package called BSTA. So you need to run this code, install.packages BSTA. You run this code once in your lifetime, unless you deinstall R and reinstall R again. But install packages, you run it just once. Okay? The one after it, library BSTA, this is a command in which you call the library. Every time you are going to run this code, you need to run this library BSTA. Okay? Unless you are within the same window and you didn't get outside of this R script, you can run it once at the beginning. But let's say, for example, I run it here, and then I go to a different R script, you need to run it again. You need to run the library command again. So just always run the library command. So library BSDA here, I have to run it again. I'm not running the install packages because I did already run it, but you do need to run it. So this is the library BSDA. So I'm going to here to do a two-sided t-test or two-tailed t-test. Same thing. Equality. Meaning I'm testing equality. So here I'm going to set the seed to 0, and this is how I create the sample. We took this command last time. So creating the sample, I put the C here in order to create the sample as a vector. And then I put R norm. 75 is the sample size. Okay, the n equal to 75. The mean equal 36,500. This is the mean of the sample. And standard deviation equal 2,000. This is the standard deviation of the sample. This is why it was important at the very beginning to set our variables to know which are the ones that belong to the population and which are the ones that belong to the sample. Because you need to know to put which values where. Okay? So here I'm going to create 3 volume, and it is going to show here. And if all of us we use the, I didn't use the set C. So let's use the set C. If all of us are going to use the set C command, that my sample is in a variable called p-value. Now I'm going to run my z-test. So the z-test here is a variable that you can call it whatever, the test in capital. Okay? Z-test is the function, z.test. This is a function, and this function you cannot play with. Like this should be written this way in lowercase. Okay? What are the arguments that I enter here? The first argument is the sample, the vector that I just created, p-value. Mu equal 39,000. This is the mu of the population, not the sample. Why? Because I'm testing against the population. I'm not testing against the sample. That's why here you need to enter the mu of the population, 39,000. Sigma dot x equal 2,000. This is the standard deviation of the population again. They are the same, by the way, in this example, but they could be different. So if they are different, the number that you enter here with the z-test is the standard deviation of the population, not the sample. Huh? And I'm going to run the test. And I don't see any results because I put it in a variable, so it's here inside this variable. So in order to see the results of the test, I just call the test the variable. And here are the results. Okay, let's see what we got. So it's a one sample z-test because I used only one sample. And in this course, till later on maybe pair t-test, but so far we are going to deal with only one sample. We are testing the mean of a sample against the population. We're not using two samples like men or men and women or whatever. We're just using one sample. Okay? So it's a one sample z-test. And you'll get different numbers here. The first number you get is the Z statistic. You took actually how to get the Z statistic, and from the Z statistic, you can go and check the tables and get the p-value, right? You took the Z table, like the table of the Z scores, and how to get the p-value from the different Z scores. So this is basically giving me the Z and the corresponding p-value that relates to this Z. Okay? So the p-value here, 2.2 times e to the power of minus 16, that means 0.15 zeros and then 22, which is basically a very, very small number, almost zero. The number of zero. Okay? P is equal to 0. And you also get a confidence interval. So this confidence interval goes almost 36,000 and 37,000. And you know that the mean of the sample lies actually in between. Like mean here lies between these two numbers. So basically these two numbers are 36,000 and 37,000, something like here. And you have your mean here or something like 36. Yeah, 36,400 is in between these two means. If you have something that is less than 36,000, that means it's outside. It's not from the same. And if you have something that is greater than, it's also from the outside, from the tails. Okay? So now p-value now is what? It's very small. It's tiny. So this is the important part that you need to know in order to interpret the z-test. You look at the p-value, and because I didn't tell you a significance level, or actually I did tell you a significance level, we want to test with 95% confidence. So that actually the significance level is 95%. Last time we said 95%, what is remaining if all the area under the curve is, all the area under the curve is what? Last time we said it. All the area under the curve is 100%. So if I'm going to look at 95%, so what's remaining in the tails is 5%. 100% minus 95, that's 5%. That's basically 2.45% from this side and 2.5% from the other side. So if I am going to look at a 95% confidence interval, I'm going to look at a p-value that is smaller than 0.05. I wanted to look at whether my sample lies in this area under the curve that is smaller, that is 0.05 or smaller. Like basically I'm asking whether it lies in the tails or not. Okay? So first thing to look at is the p-value. and if I find my p-value less than my significance level, which is 0.05, then I'm going to say that the null hypothesis is rejected. P is very small, or P is smaller than 0.05. Null hypothesis is rejected. You never say null hypothesis is accepted. Don't use the word accept with the null hypothesis at all. You either say null hypothesis is rejected if P is too small, smaller than the 0.05, our significance level, or you say, if it's not smaller, you say null hypothesis cannot be rejected. But you never say the word accept with the null hypothesis in interpreting your results. So you say P is less than 0.05, null hypothesis is rejected. So what was my null hypothesis? That mu is equal to 39,000. So if you say null hypothesis is rejected, that means that mu is not equal to 39,000. Or you can state the alternative hypothesis now. If null hypothesis is rejected, then you can state the alternative hypothesis. You can say that mu is not equal to 39,000. Okay, so that was a way to read the test just by looking at the results of the test. Okay, now the question we're asking you, okay, I want each statistic on its own, like extracted from inside the test. So I'm going to show you a way, like the lines from 10 to 13. These are ways to extract certain statistics from inside the test that you just got. So let's run attributes test here and see what it is. It gives me all the things that I can extract from the test. I can extract the statistic, which is the Z statistic here. I can extract the p-value. I can extract the confidence interval, and so on. Okay. So I wanted to extract, let's say, the test statistic, which is Z. Well, and that Z equal minus 11.05, which is basically exactly the same here. Okay. If I'm going to, let's extract the confidence interval, you are going to get the same confidence interval that you got in the test. So this is just a redundant thing that you are doing if you want, if you are asked to extract and use a certain code to extract it, but you don't need always to do that. You can just look at the test and get all the values you wanted from the test. Yeah? Any questions about the significance test or hypothesis testing equality before we go to the greater than or less than? Okay, great. Yes?
Sorry, I got a bit lost in the graph. How do you know
Which
that
graph? Oh, here?
Yeah. How do you know 26,000 and 27,000 are representing the poles?
It's not necessarily representing the poles. It's telling you that your mu should lie, if I'm going to be 95% confident, that your mu is lying between these two variables, basically.
How do you calculate those two variables?
It's actually basic. Like, did you take theoretically how to calculate by hand the confidence interval? How to calculate confidence intervals by hand? Did you take it in class? Confidence intervals, not P from Z. Because there is a formula. Yeah. Okay. So there is a formula by which you can calculate confidence intervals. Meaning, I am 95% confident that my mean would lie between two values. So this is called the confidence interval. Okay? There is a theoretical formulation for that. So basically what R is giving me is calculating it for me and giving me the confidence interval. Where is it? Where does it lie?
For the sample.
For the sample. Yeah. Yes?
What if we don't use the combine?
Okay, please raise your voice.
What if we don't use the combine function to the tree volume? You get
Which combined?
the C here. If we
Yep.
use the C, you'll be the same result.
If you don't use the C here, it is going to give you, an R norm of a distribution, but I need to check, I'm not sure, if it's going to create it as a vector or not. It's definitely going to give it to you, but is it going to create it as a vector or not? I need to check that. I think I'm like 92% sure that it is going to give you, yes, same thing. You don't need to, but you now understand why I used the C in the following example. Okay, but yeah, I think you can try it, by the way. It will give you, I think 90% sure that it will give you the same. Okay, now let's move on to the second question. second question now is something that is related to the one-tailed testing. So basically, I'm not testing here equality or non-equality. I'm basically testing greater than or less than. The mean of the sample, is it greater than the mean of the population or not, or less than the mean of the population or not? And this is used in a lot of examples or research questions. So here, for example, the question is saying a bottle filling machine is set to fill bottles with soft drink to a volume of 500 ml with population standard deviation of 25. The 500 and the 25, are these numbers for population or for the sample? How did you know? Besides the fact that I wrote population standard deviation. What else? What other clue can tell you that these are population numbers, not sample numbers?
If we are setting the parameters, then it should be population because we want that to be the overall outcome.
Yes, the word set to. So set to, that means it's the standard. Okay, the norm is whatever. Okay, so that tells you that usually if you want any, like all the times it's set to this, maybe a sample is going to give me something different, but this is what the population is giving me. The actual volume is known to follow a normal distribution. The manufacturer believes the machine is underfilling the bottles, so every time it fills them, it fills below the 500. A sample of, so he wanted to check whether the machine is underfilling or not. A sample of 40 bottles is taken and the volume of liquid inside is measured. The volumes were whatever. And here is actually coming to your question, why I used the C, because I wanted to show you in R how to create a vector. So here I'm not using randomization. I'm giving you the numbers, the 40 numbers, and I'm going to show you how to create that or to create the sample as a vector in R. The C is then going to be
So C is used to create to a vector.
to create a vector, exactly. And this is very, very common in R. Like in almost every single code in R, you are going to use the C thing to create a vector. We're going to see it now. But the question is asking me one other thing. So determine whether the bottles are being consistently underfilled using a significance level of 0.01. So here there are two things that are different than the question that was before. First, we are looking for less than. We are not looking for equal. The second thing, I am asking for a significance level of 0.01. The question before the significance level was 0.05 because this is usually the default. People usually ask for a significance level of 95%, which is 0.05. Here I'm asking for a different one, 0.01. 0.01 corresponds to what in terms of percentage? If I'm going to look like, so I said 0.05 corresponds to 95% significance level. If I'm, or 95% confidence. If I'm going to use the 0.01, this corresponds to what? 99%. Okay. That's actually going to be the 0.99. Okay. Now let's actually first state the null hypothesis and the alternative hypothesis. So what would the null hypothesis be? We haven't written.
Equals to 500.
U equals to 500. Two things important. First, equal. I told you. Null hypothesis always use equality. Even if the question is asking about less than or greater than, null hypothesis always should have an equal sign. 500 is the population mean, not the sample mean, because I'm testing against the population. So this 500 is the population mean. Okay? So for example, this sample, if you take the mean of this sample, it might not be necessarily 500. It could be 503 or whatever. This is not what I'm testing against. I'm testing against this guy. This is the important one, the 500, the population mean. Okay? Now the alternative hypothesis, because I'm not testing inequality, I'm testing less than, so the less than would go under the alternative hypothesis. So the null hypothesis is I'm testing mu is equal to 500. Alternative hypothesis, mu is less than 500. I'm looking at whether the bottles are underfilled or not. This is less than 500. Overfilled will be greater than 500. Okay. So let's go and run this thing. are the numbers I give you. So I need the C here in order to create them as a vector, and these are the bottoms. I put C and between brackets whatever vectors I have. If I want to create a vector of 1 to 3, just 1 to 3 in R, I put C between brackets 1, comma 2, comma 3. Okay? So I created the vector that is bottoms, and it is created here, and definitely all of us are going to get the same stuff because you already have the numbers. We didn't randomize anything. Huh? And I'm going to do the exact same command that I used before, but we are going to make some little changes. So first, z-test, bottoms is the sample, the vector of the sample. Mu is equal to 500, same like the last one. Mu is equal to the population mean. Sigma is equal to 25. This is the standard deviation of the population. So all that is put here is population. And then here is something new that I'm doing. Alternative equal to less. Why do I put this? Because the default in R is a two-tailed test. This is why in the first command we didn't put anything, because if you don't put anything, it will go to the default, meaning in R will understand that I'm looking for a two-tailed test. But if I want to make a one-tailed test, I'm going to put this argument of alternative equal to less in order to tell R that I'm looking for a one-tailed z-test. Z-test for now. Okay? One other argument that I added is conf.level, confidence level equal to 0.919, because again the default in R is 0.95. So that's why in this command here at the top I didn't put confidence level because the default is 0.95. But if I'm looking for a confidence level of 0.9 or 99%, I'm going to put it, I have to write it explicitly for R. Okay, clear? So now if I'm looking for a confidence level of 0.99, that means I want my p-value to be less than 1 in order to reject the null hypothesis.
1%.
Less than
1%.
1%, which is 0.01. I don't say percent, huh? Which is 0.01. So I'm going to run the test and look for the p-value and see whether this p-value is less than 0.01 or not. Okay? So here is the test. Run it. Yes.
Sorry, you said the confidence level, the default value is 95%?
The default is 95%. Yes. If you want something that is different than the 95%, you should state it explicitly. And the default is 95% because most of the research, published research papers, they accept the 95%. So that's why the researchers do that. Okay? So here I ran my z-test. This is the z statistic, and this is the, okay, confidence, before looking at the p. Confidence interval now, I have NA to whatever. What is NA? Why do I have here NA? At the time that, you remember last time I had the 36,000 and 37,000. I had two numbers.
Oh, it's one tail.
It's one tail. And because it is the less than, so it's coming from NA to whatever till 501. If it is greater than, it is going to be probably 501 till NA. These are the ways that you are going to see the confidence interval. So that makes you sure that it is a one tail, and you get the mean of the sample here. The mean of x is equal to 492.557. Now the most important number that I need to look at is what? In order to reject or accept or not accept. In order to reject or not reject the null hypothesis, what is it? Which number? No, I don't look at the mean in order to reject or not reject it. P-value. I need to look at the p-value. P-value is the thing that is going to tell me whether